So what we're going to say, sorry. So what we're going to look at here is how probability kind of compares itself to sets. If you've noticed already, I've been talking about sample spaces as a set, like the sample space of possible die rolls, and events as a set, let's say the sample space of rolling odd numbers. And so set theory plays into it, and we can think of the sample spaces as being all possible values, an event being some values within it. So let's say that this is 1, 3, 5, 4, 2, 6. This would be the sample space of all possible die rolls, and this would be the event space of odd numbers. Now, one of the things we can do is we can talk about what isn't in our event space. And we put a prime on it and we say the complement. Now, one of the things that has to happen with a probability is all possibilities have to add up to 1. And so if I were to choose anything in here, my chance of getting it would be 100%. So the probability of some event and its complement should fill the sample space. And that would give me a probability of 1, or 100%. Now, your book is going to call this complement not E, everything that's not the event. And this sets up the mathematics that we use, because we can say that the probability of an event is 1 minus its complement, or the naughty, or the complement, or the naughty, is equal to 1 minus the probability. And it's this 1 minus that we can use a lot when needed to be. So for example, if I deal 1 card out of the 52 in the deck, what is the probability that it's not a queen? What is the probability that I get something that isn't a queen? Well, the probability that something is a queen, so I'll put probability of queen. Well, there's 4 queens out of the 52, or that's 1 in 13. So the probability of not getting a queen, so queen's complement, is 1 minus 1 in 13, or 12 out of 13. And so that's the probability of an event not occurring. What we can do then is also combine events. And these kind of work together. And what can happen is, again, looking at the probability of space, and let's say I have 2 different events. Let me get this shape right. Do it like this. And so we'll say this is event A and this is event B. I actually have 2 ways this can manifest itself. I could have A or B where they share some space, or A and B where they don't. And when they don't, we call this mutually exclusive. And when we have mutually exclusive events, the probability of the probability of event A or event B happening is the same as the probability of A plus the probability of B. For example, let's say I have dice again. So I have 1, 2, 3, 4, 5, 6. I want the probability of rolling a 1, or the probability of rolling an even number. And so the probability of rolling a 1 is a 1 in 6. And a probability of rolling an even is a 3 in 6. Or I get 4 in 6, or 2/3 probability. Well, if I added up everything in here, 1, 2, 3, 4, I have 4 out of my 6 options. And so we call this mutually exclusive probabilities, and on an OR, they add. Now, if they're not mutually exclusive and they share some space, we say the probability of A or B is the probability of A plus the probability of B minus the probability of A and B, the spot that they share. Now notice this is very similar to the way we talked about sets. And so if we look at the dice example again, let's say that A is will be 2 or less. Let me change the color here so it shows 2 or less. Let me put, that's a 2 in the middle there. It's still not showing up nicely, is it? Let's see if I can get a color that pops. And so 2 or less is our over there. And then this would be odds or evens. And so we could say, what's the probability of rolling 2 or less or an even? And so we need the probability of rolling 2 or less is 2 or less, probability of rolling less than 2, plus the probability of rolling even, minus what's shared. And so the probability of rolling 2 or less is 2 out of 6, plus 3 out of 6, minus, well, they share 1 out of 6. And so that again gives a 4 out of 6. But I chose it that way, or 2/3. And so we can combine probabilities with an OR by adding. And so when you OR something, you give yourself more and more choice. And your probabilities go up. And so ORs are our ability to get closer and closer to 1. Well, if we can OR something, I've already talked about ANDing something. And ANDing is what happens when we only talk about probabilities when they share a space. And so if an event is independent, and we want the probability of A and B, then we look at the probabilities multiplied. And so two events are independent if the effect of one doesn't affect the other. So a roulette wheel has 38 slots. A roulette wheel can never spell it right. Roulette wheel has 38 slots. 1 through 36, 0, and double 0. 18 are black, 18 are red, and 2 are green. And so it can land on any of the 38 slots. So the wheel has 38 likely outcomes, thus the probability of red occurring on a play is 18 out of 38, because there's 18 red. And so if I play 2 games of roulette, what's my probability of rolling red and red again. Well, on the first game, I have 18 out of 38. And on the second game, I have 18 out of 38. Which, what is this? This is 9 out of 19 times 9 out of 19, which is equal to 81 out of 361, or 0.224. Now, ands do the opposite of ors. The probability goes down. We want something to happen after another event. We want independent events happening. Then in the probability goes down. And so anding something, or wanting very specific things to happen in order, gets rarer and rarer. Now, if events are dependent, then in what we have for the probability of A and B is the probability of A times the probability of B given A has happened. Because A is going to change the probability of B. I always kind of think of this in a card way. And so what I want to do is I want to look at an independent and then a dependent. So there's 52 cards in a deck, and 4 of them are queens. And so I will draw a queen, or I'll draw a card. And so I'll say, what's the probability of drawing a queen on my first? That'll be A. And then I put the card back in and I reshuffle it. And what's the probability of drawing a queen again? And so the probability of A and B in this case is the 1 in 13 times 1 in 13, or 1 in 169. I have a 4 in 52 chance of drawing a queen, and the second time around I have a 4 in 52. But that's because I replaced the card. Say I do this again, but I'm going to say that for A, I have the probability of drawing a queen, and now I don't replace the card. And so now my probability of drawing a queen, and let's say the probability of drawing a 4. So I draw my first card, and my chance of getting a queen, and then after I draw the queen, my probability of getting a 4. Well, when I go to first draw the queen, the probability of A is equal to 4 in 52, or 1 in 13. Now the probability of B now, though, because I've already pulled one card out of the deck, one card is already out of the deck, is 4 in 51. Because I've removed one. And so the probability of A and B, given that B is affected by A, is 1 in 13 times 4 in 51. And I have to run over to my calculator here. We'll get a crazy decimal for this, I know. I get, less than 0.006, 0.033, ... And so 0.6% chance. And this is given that the initial event happened. We call this conditional probabilities. And conditional probabilities get a probability of B given A has happened. And we use the pipe. And what conditional probabilities do is that we update our information. We change B based on what has already happened. And the nice thing about probabilities is they can track information. This works really, really well when we go back to the graphs we were doing. So I'm going to make another graph here. This is a survey on breast cancer. And we'll graph out the responses on the survey and the data, and we'll look at the totals that come through. So we'll have breast cancer, no breast cancer, and this is on a positive mammogram and a negative mammogram. And so we're kind of tracking the error and how the error affects itself. And so there were 100,000 samples looked at. And so let's see. This is 100,000 women 40 to 49 who participated in mammogram screening, and these were the results. And so we want to know the probability that you had a positive mammogram given no breast cancer. I'll just put no BC. And so we start with the given. So we're given here, so we now limit ourselves to this column. And so for this case, we only have 99,200 because by given no breast cancer, we've limited ourselves to here. And so what we're looking at is 99,200 possibilities. And we're looking for the 6,944 because we want a positive mammogram out of that, or about a 7% chance. But we could say this around. We could say that what's the chance that there is no breast cancer given you've had a positive mammogram? So now we limit ourselves to the positive mammogram here. 7,664, and no breast cancer 6,944. Or a 90.6%. And so notice the given talks about our level of current knowledge, and it limits, it acts as a screen on what we can see or access in information. And so conditional probabilities are a way to update the information that we have. The last thing I want to talk about in probabilities are expected values. And an expected value is if I were to play a game of chance or run through some mathematical formulae, then in the expected number I get could be fine. So for example, let's say I have a die which has the numbers 1, 2, 3, 4, 5, and 6. What's the numbers themselves all have a 1 in 6 chance of happening, but I want to know what number I am expected to roll. What would be if I were to go, what number, would I get a 4 on average? If I rolled 100 times, what would be my average? And what happens is we multiply the value times the probability for each outcome. So I have 1 times 1 in 6 plus 2 times 1 in 6 plus 3 times 1 in 6. So each value times its probability. And so we add all of these up, so that's 1 6 plus 2 6 plus 3 6. So 1 6 plus 2 6 plus 3 6 plus 4 6 plus 5 6. So 11, 15, 18, 20, 21 sixths, or 3.5. And so the expected value of rolling a die is 3.5. That means if I roll dies over and over again, that should be my average. And so the expected value is the total, the sum of each of the probability of an event times the value of the event. So let's look at another one. Let's look at, I'll go to an example in the book here as I move through. Yeah, I like doing this with gambling games, so I'm going to do example 5 in the book. So if you're using one die, and if the die is rolled and shows 1, 2, or 3, 1, 2, or 3, you don't win. If it shows 4 or 5, you win $3. And if it shows 6, you win 9. And it costs $1 to play the game. And so what we want to know is, well, here we have a probability of losing. Probability of losing, you have 3 and 6, or 1/2 chance of that. And it has a negative value, -1 times 1/2. Now the probability of winning $3 is 2 and 6, or 1/3, and so it has a value of 3 times 1/3. $3? Yep, $3. And then if you have $9, oh wait, but you don't win $3. You've spent $1, so I have to take 1 off of that, right? You win 3, but it's cost me 1. And then in the probability of winning $9 is 1 in 6, but that's going to return me $8. 1 in 6. And so now I can add up all that's possibly happening. So -3 plus 4 plus 8 all over 6. Right, if I'm turning in all these denominators into 6s, so I have 2 6s or 4, 3 6s, which is -3, so I got 12 9/6, or 1.5. And so my expected values, I could expect to win $1.50. Well, if I were the gambling house designing this game, that would be a bad game. In fact, what they do when designing the payouts for games is they make the expected values negative. Because if the expected values are negative, the house always wins. Alright, so this is probabilities and expected values, and we're going to build these into the ideas of statistics in the last set of lectures. Play with the combinatorics on here. Get used to how quickly numbers add up, because that is the important thing with this, is getting used to these large numbers that come from small things.